Hey everyone, today we're going to solve this equation where we're going to have to use trig identities for both cos 2 theta and sin 2 theta to make this equation solvable. So we could start with the numerator, the cos 2 theta, but if you have them handy, you'll remember that cos 2 theta has three different possibilities for its identity, whereas the denominator, sin 2 theta, has a 1. So that might be a nice place to start. Let's leave, that's not necessary. Let's leave the numerator as it is, 1 minus cos 2 theta, and let's use our identity for sin 2 theta to turn it into 2 sin theta cos theta. Okay. Now, that means that we have a nice denominator that is just one full term, right? And in the numerator, we have to make a thoughtful decision on which variation of our cos 2 theta identity we might use. Now, it doesn't matter which one you go with, but there will be one that will get you to where you want to be fastest way possible. So I'll maybe give you a second to think about what choice might get you to be able to solve this equation in the fewest amount of steps possible. I'll just point out that we have a 1 minus that identity going on, right? If we use the sine cos squared minus sine squared, we're going to have 1 minus cos squared minus sine squared, which might actually be fine. If we use 1 minus 2 cos squared minus 1, we'll have two terms, which is, again, we'll eventually get to where we need to be. But I'm thinking that if we use the cos 2 theta is 1 minus 2 sine squared, we'll have 1 minus 1 minus 2 sine squared theta. And right away, the ones are going to cancel out. And so we'll just have one nice term in the numerator, which is as easy as it gets, right? And so I encourage you to do the same, or you can try one of the other variations and see that you will get there eventually. It just might take an extra step or two. So now our numerator simplifies down to the ones cancel out and minus a negative, right? This becomes positive 2 sine squared theta over 2 sine theta cos theta. And now we can only cancel out factors that are common to every term in both the numerator and denominator, since both the numerator and the denominator have only one term. We can cancel out any factors that are common to both. You'll notice that there's a sine theta factor common to both, so this one cancels and the squared on the numerator term cancels, and the 2's clearly cancel out as well. And so all we have left, I'm so sorry, this is equal to root 3. We're solving an equation here. Let's not forget about that. So now our left-hand side simplifies down to sine theta over cos theta, and that must be equal to root 3. Now, this might still look a bit tricky, but I'll remind you that we have a simpler expression for the ratio of sine theta over cos theta. That's our tan theta ratio. And so we are really solving the equation tan theta is equal to root 3 on the interval negative pi to pi in radians, right? Now, before we get into finding our solution set, we should be mindful of any non-permissible values, right? Any values that are not allowed to be inside our solution set, because they would create a denominator of 0, which would make this entire equation invalid, right? And so any non-permissible values, which we have to be mindful of, originate from a denominator of 0, meaning that our sine 2 theta is 0, right? This is a straightforward enough equation to solve. We know that 2 theta would therefore be the inverse sine of 0. Let's keep all general solutions because we're going to divide by 2. Let's just be safe. So that means that 2 theta would be the inverse sine of 0 is on our unit circle. That's the y coordinate. That's 0, pi, 2 pi, 3 pi, right? So 0 plus any multiple of pi radians. So plus pi k for any integer value of k. One more time, that's z. Oh, z is the set of integers. So k can be any element of the set of integers, i.e. k can be any integer, right? We don't put the minus because integers can be negative, and so that would be redundant, right? And now that's 2 theta. We want to solve our solution set for theta, so we should have our NPVs in terms of theta. Let's divide everything by 2. So our NPVs are all going to be of the form 0 over 2 is 0. I'll just omit that part. Pi over 2k meaning any integer multiple of pi over 2, for k being any integer value. Those are our potential non-permissible values. So let's just keep that in mind as we finally get our solution set. So I'll box these off. Okay. Our solution set here is the inverse tan of root 3. And we know that on this interval, and for any interval, tan has positive values in quadrant 1 and 3, right? Q1 and Q3 is where we should expect any and all of our solutions. And so now I'll ask you to think, where is tan theta positive root 3? Well, in Q1, through the positive angles, that is at pi over 3. So we get theta is equal to pi over 3. But through the positive angles, if we have to stop at pi radians on the left side of the unit circle, we will not even touch Q3. And so that's the only solution we're going to get through the positive angles. Now, let's draw out the unit circle really quickly so we can imagine our second solution. This serves as a reference angle, right? If we use that reference angle in Q3, that's going to look something like that, right? That is going to be our reference angle of pi over 3, right? And now we can go through the negative angles, meaning that we go from the positive x-axis clockwise, right? And if we do that from here over to the terminal arm where our second solution, our solution in Q3 would lie, we know that this angle measured through the negative angles clockwise from the positive x-axis is going to be negative pi plus pi over 3, right? Negative pi would take us here, plus pi over 3. That, in standard position, gives us an angle of negative 2 pi over 3. And that is well within our interval. And so that is our second solution. Now we should verify to make sure that these two solutions don't fall inside the set of non-permissible values. Our set of non-permissible values are all of the form pi over 2 times k for integer values of k. There is no integer multiple of pi over 2 that would ever become either of these solutions. And so our solution set is safe. And here are both of them. And we're done. So I hope that helps. And thanks for watching.